Okay, and example 4. Evaluate the integral of the indefinite integral of dx divided by x squared times 9 minus x squared. Okay, you can play with this for a while. It doesn't fit any of the arctan, any of the inverse trig functions formulas. You can do u substitution. You run into a wall if you try to do complete u substitution as well. All right, I'm going to show you something that kind of looks crazy at the beginning, unless you've seen them in other calc classes. I'm going to perform a different type of a complete substitution. Instead of introducing a variable and setting it equal to an expression in terms of x, I'm going to let x equal to an expression in terms of another variable. And I'm going to explain, I'm just going to give you the substitution for now, but I'll explain what it would, more systematic way of approaching this. All right, so I'm going to start by writing the problem. What if you let x equal 3 sine of theta? Okay, so again, this is a different type of substitution. Instead of introducing a variable and setting it equal to an expression in terms of x, you're letting x equal to an expression in terms of a different variable. All right, I'm going to let x equal 3 sine of theta and see where that takes me. Well, if x is equal to 3 sine of theta, dx equals 3 cosine of theta. All right, I am with you so far. X squared is 9 sine squared of theta, which means this little expression under a radical, 9 minus x squared. 9 minus x squared is 9 minus 9 sine squared theta. Factor out a 9. 9 times 1 minus sine squared theta. This is, of course, cosine squared theta. All right. So if I actually put in my substitution, so dx is 3 cosine theta d theta. Sorry, I should say d theta. X squared is 9 sine squared theta, and the square root of 9 minus x squared becomes the square root of 9 cosine squared theta. All right. And then, of course, I'm going to simplify. The square root of 9 cosine squared theta is 3 cosine theta. The 3 cosine theta cancels out. You get d theta divided by 9 sine squared theta, which is 1/9 cosecant squared theta d theta. And then, of course, we know that that is one of our standard integrals, because it's one of our standard derivatives, so we can just remember the result in reverse. That's equal to, the derivative of cotangent is negative cosecant, right? So the integral of 1/9 cosecant squared theta d theta is negative 1/9 cotangent theta plus c. Why did this work? Because of the Pythagorean theorem. You have things added or subtracted. If you have a sum of squares or a difference of squares under a radical, this trick will work, because there's 3 Pythagorean identities, right? And I'll show you what the substitutions are. You can make it work for either a sum or a difference of a variable squared and a constant squared under a radical. All right, so now we got a bit of a problem, because this was an indefinite integral. If this was a definite integral, I would change the bounds right away as well, and then not having to worry about x anymore. But this is an indefinite integral, so whoever proposed this problem gave it to you in terms of x. You can't give them the answer in terms of theta. We've seen this trick before, how to recover our x back. We don't want to go to the we don't want to start taking inverses of things, because then the algebra is messy. So we're going to kind of go back to geometry. We're going to say if x equals 3 sine of theta, that means sine of theta is equal to x divided by 3, which means there exists an angle theta so that its sine is x divided by 3. So the opposite sine is x, the adjacent sine, the hypotenuse is 3, and then the adjacent sine is 9 minus x squared. The missing side of the triangle is always going to be whatever is under whatever the radical term is. It's just the way these are kind of cooked up. So that means if you want the cotangent of that angle, it's going to be adjacent over hypotenuse, or square root of 9 minus x squared over x. And then you got the negative 1/9 plus c. All right, and then you can rewrite it more compactly. All right, so that's your answer. This seems too good to be true. Is this really the antiderivative of this integrand? We're going to check just with the derivative, and then I'm going to give you I'm going to give you the rules for trig substitutions. So we're going to check. All right, we're going to check that the integral of dx divided by x squared times the square root of 9 minus x squared is in fact negative square root of 9 minus x squared divided by 9x plus c. All right, and then the way you check is you take a derivative. We're going to apply the quotient rule, low d high. So minus chain rule, minus 2x. We'll bring the 1/2 in front, 9 minus x squared to the negative 1/2. Plus minus high d low. So we got 2 minuses divided by low squared. 9x times negative 1 times negative 2x times 1/2 is 9x squared. Plus 9, the square root of 9 minus x squared over 81x squared. Multiply the numerator and the denominator by the square root of 9 minus x squared. Get 9x squared plus 9 times 9 minus x squared. And then in the denominator, 81x squared times the square root of 9 minus x squared. Distribute the 9, combine like terms, and divide out 81. You do get 1 over x squared times 9 minus x squared. So that is, in fact, the antiderivative or the integral of this. All right, and here's the rules for trig substitution. Okay, so that does check out. This is the rules for trig substitution. This is a whole lesson in Algebra 2 college class, just because the algebra is so complex. So if you have, as I said, a sum or a difference of a variable squared and a constant squared under a radical, you can use trig substitution. And the reason is because of the Pythagorean identities of trig functions. Okay? Now, the reason why there's 3 is because you can either have the variable term squared minus the constant or the constant term squared minus the variable squared. But you would perform these substitutions. All right. You can do a little bit of you can draw triangles and do a little bit of geometry with Pythagorean to kind of see why the ones, these ones match up in particular. It just has to do with what their corresponding trig identities are. But these are the trig substitution formulas. Sometimes it works when you don't have a radical either, okay? That's the thing about integration. It's just a bag of tricks. So substitution is a powerful trick in math. There's some pretty interesting problems you can solve by transforming them to a different type of problem first. But all right. So I just have those 4 examples and then a list of techniques for you. So now you're ready to work on a problem set for this lesson. I'm going to make it due on Monday, so next B-Day, March 30th by 9 a.m. I put some interesting ones in there just because you are a clever class. All right.